All right, let's look at this situation. We have given here a plastic ball, radius r prime, and it floats in water with 1/6 of its volume submerged. So, like, there's just a piece of information that's thrown out there. You can do different things with this piece of information. If you are like me and your brain likes pictures and you're fairly visual, I would rate at this point draw that out. What would that look like? 1/6 submerged. So you'd be like, okay, well, they're giving me something like this. It has a radius r prime, and when it floats in water, it floats with 1/6 of its volume submerged. All right. So we know that's 1/6 of its volume. Okay, that will probably come in handy at some point somewhere in the problem. Moving on. Determine A, the force that must be applied to the ball to hold it at rest, completely submerged. So you can maybe imagine this if you played in a pool or whatever with a beach ball or some kind of ball that floats. It's sitting there on the top, quote unquote, top of the water, and then you can put your hand on it, and you can submerge it, right? You can push it down under the water. We've probably all done this with buoyant things. And what's being asked here is how much force does it take in this case to do that? Part B of this problem asks, like, say you push it all the way under the water and then you let it go, and then you know exactly what's going to happen if you've, again, played in the water a whole lot, that the ball will come shooting up out of the water. So question B asks, what is the ball's acceleration at the instant it's released? And I'm just asking there about the instant it's released because I don't want us to be worrying about the drag forces in the water. That's a whole different problem, right? The dynamics of that. So we're going to let that go. But what just focusing on the forces then, what is the ball's acceleration at that instant? Okay. Um, so we're given r prime, the radius of the ball, and the density of water. So let's just kind of maybe turn our attention to this part A here. And now we're thinking about the ball being totally submerged in the water, right? So in order to do that, like say here's the surface of the water, and now I've got it completely submerged, radius r prime. And in order to do that, I know that there has to be an applied force on it because the ball's not going to do this by itself, right? I know that, like, if left to its own devices, it'll float with 1/6 of its volume submerged there. And of course, it has to have some amount, it has to be displacing some amount of fluid here because the ball will have some amount of mass, right? So let's think, all right, well, let's just call this some applied force here. I'll call it F prime that I'm applying onto the top of this thing. Cool. So I can draw a free body diagram for this situation. And this is for the part A, right, which is the submerged case. And we can represent that. So what are my forces here? Well, I know that I'm very excited to use the buoyant force, right? This is like, oh, my new thing called the buoyant force. So I'm going to say, well, there's this upward force, which is buoyant force. And then I have downward, I have the weight of this ball, whatever that is. And then I have this applied force that I'm calling F prime here, right? And we're just holding it at rest down there. So there's not going to be any acceleration going on here. This is just you kind of pushing the ball under the water and holding it there, thinking about that. Okay, so with that information, we can sum everything up. Use second law here. Buoyant force minus weight minus F prime equals ma. Acceleration goes to 0 in this case. This is, again, a static equilibrium case. So I can solve for my buoyant force is equal to the weight plus F prime. Fairly simple there. So now, after you've done this essential force analysis part, now is when I want you to turn your attention to Archimedes' principle. Because again, remember, all Archimedes' principle does for you is gives you the magnitude of the buoyant force. Archimedes' principle does not relate to your free body diagram. It doesn't relate to your force analysis in any other way, right? Archimedes' principle doesn't give you directions of forces or talk about causation or any of these other things. I just want you to keep it in perspective. So you still need to do all of the same thinking you've always done for force analysis, and that is you get your one invisible force, and then everything else must be a contact force. So identify your forces, apply second law. The new piece is your applying Archimedes' principle in order to find the magnitude of buoyant force. So I can say here, by Archimedes' principle, buoyant force is going to be equal to, now remember what this is, the weight of the displaced fluid. The weight of the displaced fluid. So I can express the weight of the displaced fluid by the density of the displaced fluid, right? The volume of the displaced fluid. So this ball is going to displace its own volume in water when we submerge it. So the volume of the ball is equal to, because it's completely submerged, the volume of the ball is equal to the volume of the submerged fluid. So that'll be 4/3 pi r prime cubed, since it's a sphere. I multiply that by little g in order to make it a weight. Yeah? So that gives me the magnitude of my buoyant force. So this then I can sub in for buoyant force in my Newton's second law equation. And remember that I'm trying to solve for F prime, right? That's my goal here. So if I sub this in, what do I get? Density of water times 4/3 pi r prime cubed times g minus mg is equal to F prime. So I see that I'm kind of am making progress on getting to F prime, but what's standing in my way right now, I mean, R prime is given, the density of water is given, the mass of the ball is not given. So I need to do something about that, right? The mass of the ball is not given. So I'm not done with, I can't fully express F prime. All right. So now I'm going to turn my attention back to that first line in the problem statement here, which tells me this information that I figured I'd have to use somewhere. And that is that the ball floats in water with 1/6 of its volume submerged. So here, this is the floating case that I have drawn over here on the right. And now I better analyze this. So let me do a free body diagram of the floating case, right, of the ball floating. So how I extract information is the same as I always have. I draw a free body diagram, I apply second law, and then I can extract some relationships from that. So we'll still do that. So in this floating case, what are the forces? Well, I've got the weight of the ball, and then I've got the buoyant force here. And I'm actually, because I already started using primes over here with the F prime, I'm going to prime the submerged buoyant force and leave this buoyant force unprimed. I don't want to use the same symbol for both of them because they're different, right? The buoyant forces, they both are directed upward, but they're going to have different magnitudes, aren't they? So in this floating case here, my second law statement would be fairly simple, wouldn't it? Buoyant force minus weight equals ma. This goes to 0. So buoyant force is just equal to the weight of the ball. And now, again, I do my full second law analysis, and then I go to Archimedes' principle, right? So by Archimedes' principle, and I'll do this in green here, my buoyant force is equal to density of water, volume of the displaced fluid, because remember, I'm trying to express the weight of the displaced fluid. So in this case, the volume of the displaced fluid is 1/6 the full volume of the ball, isn't it? So that's going to be, I'll put this in brackets, 1/6 times the ball's volume, 4/3 pi r prime cubed times g. So you can see that these two buoyant forces are not going to be the same. We are displacing different amounts of fluid, right? Therefore, those buoyant forces won't be the same. What this allows me to do then is to solve for m. I can do some algebra moves here and I'm able to solve for m. M is equal to 2/9 rho of water pi r prime cubed. And now that I have that expression for m, right, I can take that expression for m and I can substitute it in for m over there, and I will be able to solve for f prime. So that allows me to answer part A. And when I do that, what I will get is f prime is equal to 10/9 rho of water pi r prime, r prime cubed g. So super important to keep track of things. You see, you're going to have, some new symbols. The rows, the densities are new. You got to keep track of density of what. I usually subscript for that. So some of that might feel a little bit different, but overall it should feel very similar to what it is that you've been doing. All right, let's move on to part B here. So part B asks us to find the ball's acceleration at the instant it's released from complete submersion. So you push it under, again, I want you to think about this physically. You push the thing underwater and then you let it go, and you can kind of imagine that then it's going to accelerate upward, right? So now think about what's different about the free body diagram then. So this would, if we were to draw a free body diagram for part B, right, it's submerged, but now there's no force holding it down, right? There's that F prime goes away because you move your hand and you're no longer pushing it under the water. So this is a dynamic case, which means it's not in equilibrium. So what do we have here? We've got downward force, only the weight, and then upward force, buoyant force, and this is going to be buoyant force prime here, right? Because it's fully submerged, so it's the same buoyant force as we found when we were solving for part A. So now, and my acceleration is going to be upward. I'm going to make upward positive. What I can say with my second law statement here is that buoyant force prime minus mg equals ma. Now I'm interested in A, what that is, right? So buoyant force prime, remember, like I know what that is now. I've got that. It is, and I found that down here, remember? So super handy. So I can sub that in for my buoyant force here. And there's also m as an unknown, but remember that we found m, right? So this m down here, I can sub in for both these masses, and then I will be able to solve for the acceleration there. And you've done enough of these force analysis problems here and substituting in different forces and such that hopefully that'll be fairly straightforward. The big conceptual move there was to remember that now that f prime is gone and that you're no longer in equilibrium.